All right, welcome back to Anatomy and Physiology with Dr. H. This is video number 3 for hemostasis. If you have not watched video 1 or video 2, I do recommend going back and watching those before watching this one. It just helps with the context of the situation. But in essence, we are stopping the bleeding with hemostasis. Post-damage, tissue damage, we need to first stop the actual bleeding by vasoconstricting. It's called a vascular spasm. Then we need to block the damaged area. So we go through platelet plug formation. And here we are on video 3 where we're going to be talking about coagulation, which is the process of tying down all of the debris that's in the bed of the truck. Right? Driving down the freeway in order to keep your stuff from just flowing and flying and doing all sorts of crazy things out of the bed of your truck. We got to tie it down. So we're going to need some fiber mesh here. Now, this is a complicated, quite a complicated theory here. Lots of steps that are involved in this. But in essence, what I want you guys to be able to kind of look at is that at the end of the road, we need to create a fiber mesh. So we're going to be creating a fiber, but of course is the human body, so we call it fibrin. It's a protein fiber. And we're going to be meshing it all together, so we're creating a polymer. So this is a fibrin polymer. And fibrin polymers are made out of the protein called fibrin. Fibrin is an active protein. It's a functional protein that is actually produced from another factor that's involved in coagulation. That's called fibrinogen. And I started to mention this in the previous video, so go back and relearn a little bit about it. But in essence, it's produced by the liver, secreted into the blood, taken up by megakaryocytes, stored inside of our platelets, and then we also have fibrinogen just in our bloodstream as well. So fibrinogen is the inactive form of fibrin, and what we're going to need to do is we're going to need to figure out a way to activate fibrinogen. So we're really going to want to run this chemical step where we cut the ogen off of the fibrinogen, and this is where things get a little bit more complicated. And yes, I'm working backwards on a flowchart. You're welcome, actually, because sometimes working backwards is a lot more efficient than working forwards through a flowchart. It just makes it simple. We know what the end story is, and we know that we need to walk our way backwards to the beginning of the story. Beginning of the story is tough. End of the story is easy. So what runs this chemical reaction? Well, it's another protein. Okay, the protein that we're going to be using here is called Again, thrombo in Latin means to clot. So now we got a protein that is our major clotting protein. It's called thrombin. But thrombin is most definitely not active in your bloodstream all the time. If it was, we'd be creating fiber meshes all the time. We can't have that. We can only clot when we need to clot. Only when a bunch of other things have happened first. So instead, what we have in our blood most of the time is called factor 2. What is factor 2? Factor 2 is actually called prothrombin. And if you haven't taken chemistry or biochemistry class, you may not know that pro is just another way of saying that this is an inactive protein. So if we start the word with pro, then it is inactive. And just as a quick recognition, we also said that if we end a word in ogen, then it is also inactive. Basically, it's just whether or not we are inactivated on the amino side or the amine group side, or whether we are activating it or inactivating it on the carboxylic acid side of an amino acid. That's all that is. So we need to take prothrombin and we need to turn it into thrombin. So what are we going to need to do? We're going to have a chemical reaction that takes off that pro. By the way, I mentioned it, but I didn't write it down. This is also known as factor 2. Whereas fibrin is derived from fibrinogen, and fibrinogen is factor 1. There's 13 different factors that are involved in this process, so you don't need to memorize them all. We're going to come back and fill in a few more blanks as we go through this as well. So how do we get prothrombin to become thrombin? Well, we're going to need another chemical reaction that allows this to occur. So how do we get prothrombin to become thrombin? We're going to need to take off that pro. Well, good news, we have that ability through something called prothrombin activator. The name literally tells you what it's doing. So we're going to have an arrow that is running this chemical reaction, and this is coming from prothrombin activator. I can't remember if I mentioned this because, you know, brains and stuff don't always remember it. This is what they said 5 minutes ago. Prothrombin is produced by the liver, just like fibrinogen is produced by the liver. So what do we need in order to activate prothrombin? We need a prothrombin activator. Prothrombin activator is going to take the pro off the thrombin, leaving us with thrombin. That's fantastic because now we have a protein that can start to activate fibrinogen. How does it do that? It takes off the ogen to become the fibrin, and a lot of fibrin combined is called a fibrin polymer. Yes, awesome, wonderful. What do we need in order to activate this fibrin polymer, you may ask? Well, we're going to need something else down here as well. It can't just be fibrin alone. That's not going to work. Thankfully, we don't want polymer meshes to be built when we don't want them built. So we have to have another set of steps down here that activates this part. There's going to be another factor, not factor 2, not factor 1. We got a weird one. It's called factor 13. Okay, great, 13. How am I supposed to remember that? Okay, factor 13 is just called fibrin stabilizing factor. It is stabilizing fibrin, allowing for fibrin meshes to be produced. What else is required in order to do this step? Good old calcium. Calcium, secondary messenger, important in so many different things. That's required for this step as well. Whereas now this prothrombin activator, this is going to have some steps that are required to run it. We're going to talk about those in just a second. But again, I'm working my way backwards because I do think that this particular flowchart that's on here is much easier to learn than starting from the very top. So the last part of this smaller flowchart that I want you guys to be able to think about is the fact that thrombin is actually quite powerful. This guy right here is called thrombin for a reason. It's kind of one of the major clotting proteins in the body. Thrombin, once it's activated, yes, it's going to go down and help the ogen get cleaved off the fibrin, but we also now need more thrombin because we need to make this happen, and we need to make this happen fast. So the way this does this is actually through a positive feedback loop where thrombin is going to go back and start to activate even more prothrombin activator. Thrombin acts with positive feedback. And it does this in the presence of another factor. Of course there is. This factor is called factor 5. And factor 5, I don't know, it's got a weird name. It's called the labile factor. It is a cofactor that is going to start to activate the prothrombinase. Prothrombinase is an enzyme that is going to be your prothrombin activator. So, sweet. Factor 5 is involved here. So now, depending on who your professor is, you may need to know more of this flow chart. You may only need to know this much of the flow chart. I'm going to go ahead and give you guys a second, take a screenshot. Many of you are just going to need to know this part of the flow chart. Great, okay. We now have a screenshot of this, but prothrombin activator isn't always active. We're going to have something that activates it. What activates prothrombin activator? Another factor called factor 10. My 10 kind of looked funky there for a second. Of course, it's Roman numerals. Factor 10. All right, factor 10 is also known as the Stewart-Prower factor. Stewart-Prower, P-R-O-W-E-R, not power. And basically, this factor 10 is going to also be activated by other factors. But once factor 10 is active, it is going to be trying to talk to the prothrombin activator. But it can't do it by itself. It actually needs some other things to help with this process. There's so many steps in this. One of the major factors that is involved in this is prothrombin. So prothrombin's already in your bloodstream. And in order to activate prothrombin activator, we need prothrombin to be present. And prothrombin will be communicating with this step right up here to activate more prothrombin activator. Remember, prothrombin is also known as factor 2. So what is required? What is one of the requirements for this step right here? Factor 2. I forgot to put an arrow here, but there we go. No, that's the ugliest arrow ever. There we go. Still ugly. All right, so now what is required for factor 10 to start to activate prothrombin activator? Factor 2. But guess what? We ain't done yet. What else is required here? We need some calcium, just like down here. We need some factor 5. And we need some platelet factor 3. If you go back and watch the video on platelet plug formation, you'll see this is part of the final products produced by activated platelets. So all of these things are required in order to activate prothrombin activator. If any of these steps are disrupted, we are no longer activating this prothrombin activator. Prothrombin no longer gets converted to thrombin. Thrombin can act as a positive feedback loop for prothrombin activator, and fibrinogen is not going to get turned into fibrin in order to become a fibrin mesh. It is a complex web. Ironic, because it's a web of fibrin, right? So most of the time, factor X is inactive. Thankfully, we need all of these steps to occur in order for the fibrin mesh or fibrin polymer to be created. So how do we go about activating factor 10? Well, this is where it kind of depends one more time on who your professor is. So without going into too much detail, an old school thought process for factor 10's activated, there's a lot of theories on this. It's really hard to study it in complete, statistics and medical journal stuff has there's a lot of work that has to go into trying to study these different pathways. So a previous understanding of this is that it involved an intrinsic pathway and an extrinsic pathway, a local inside of the blood vessel pathway, and another pathway that was instigated by the collagen matrix that gets damaged. Now, that should be effective for most of y'all, okay, where there is going to be an intrinsic pathway and a extrinsic pathway. That's not a T, and I didn't use my erasable markers. I started doing pathway. Extrinsic pathway that are going to be required to activate this factor 10. Now, that being said, if we were to try to follow this because your professors might ask you to, there's going to be a bunch of steps. The intrinsic pathway requires a factor 12. Factor 12 is the Hegeman factor, and basically it's going to be instigated by activated platelets. Factor 12 then goes on to activate factor 11. Factor 11 is also known as the plasma thromboplastin anecdents. So whatever the heck that is. I never studied it in a lot of detail. Factor 11 is going to go on to activate factor 9. Factor 9 is also known as the anti-hemophilic factor B, or the Christmas factor. And factor 9 is going to activate factor 8. That's right. We got this. Factor 8 is the anti-hemophilic factor A, and it's once factor 8 finally gets activated that the intrinsic pathway is able to communicate with factor 10. A lot of stuff are required for these pathways to be running. Things like calcium, you keep seeing that, PF3. Both of these are required to run this step right here where factor 9 is getting converted into factor 8. The extrinsic pathway, this is damage to the collagen matrix that's out there. What's going to happen out here is as the collagen matrix gets damaged, tissue factor, like that's his full-on name, is going to be activated. This is factor 3. So, but often it's just known as tissue factor. These are all factors, but the tissue factor is factor 3. And then this guy here is going to be a major player in the coagulation step, pretty much no matter what, depending on whether you're old school following intrinsic and extrinsic pathways, or whether you're looking at some of the novel new pathways that are out there. This tissue factor is going to combine with another factor, which is called factor 7. This is a stabilizing factor, or a stable factor. So factor 7. And these two combined are going to go and help with factor 10. A lot simpler pathway here. What is required for this pathway to run efficiently? Calcium. Fantastic. There's only one more thing to discuss up front here with hemostasis and this particular part of hemostasis and creating a coagulation impact, and that is that there's a vitamin that you get from your diet that is digested by in your large intestines by your bacterial colonies called vitamin K. And vitamin K, I'm going to go ahead and as a key, I'm just going to have vitamin K with an asterisk next to it. And I'm going to show you that there's a bunch of steps that are vitamin K dependent. Anytime we're dealing with factor 2, prothrombin is vitamin K dependent. Another one that is vitamin K dependent is factor 7 up here. So vitamin K is required for this part of the pathway to run. Another part of the pathway that requires vitamin K is factor 9. And the last one is right here with factor 10. All of these parts of the pathway require vitamin K. Now, for my students, I don't require you to memorize that. The idea here with vitamin K is that we have to get it from our diet. We cannot actually produce it in our body, and we can't even digest it ourselves. We need bacteria to digest it, and then our large intestines will absorb it. So now if we end up being vitamin K deficient, if this pathway cannot run, coagulation doesn't occur, and this is going to end up causing some sort of hemolytic event. We're going to have basically nonstop bleeding. And in fact, if we block vitamin K absorption in the gut, this is one of the old properties of rat poison. So then animals would eat it, block vitamin K absorption, and they bleed out internally. So fun way to end this particular video, but here we are. Coagulation. This is video number 3. Now, this whole entire time I've been saying there's going to only be 3 videos for hemostasis, but in fact, we're going to make a 4th. And in the 4th video, what we have to do, we're going to have to break down this fibrin polymer once the tissue heals. So right here, the tissue starts to heal. But once it's healed, what do we not want anymore? We don't want this fibrin polymer. So we're going to have to go in with a bunch of scissors and cut this gigantic fiber mesh. For that, we're going to need another factor, which we'll discuss in another video. Thanks for listening. Be both human and kind.